Hi, thanks so much for accepting my abstract and for attending my talk today. I'm really, really sorry I couldn't be there in person, but I'm still excited to tell you about my and my collaborators' recent discovery of calcium, cerium, titanium, manganese oxide perovskites for two-step solar thermochemical hydrogen production. So this was a multi-institutional collaboration. Many researchers worked on this project. Some of them are in the audience today, and that makes it especially sad I couldn't be there in person because I was really excited to meet some of you. Okay, so two-step solar thermochemical hydrogen production cycles using off-stoichiometric redox-active metal oxides like CeO2 potentially offer a cost-effective, sustainable route to carbon-neutral hydrogen. So here on the left, I'm showing a recent techno-economic analysis by Budama, Johnson, Ermanowski, and Stechel, which shows on the y-axis hydrogen production cost in US dollars per kilogram, and on the x-axis a series of different considerations that could lead to a reduction of the current price, which is $4.5 US per kilogram hydrogen, to somewhere around $2 per kilogram hydrogen. Oops, sorry. But that's still 2 times the value targeted by the DOE in their hydrogen shot, which is set at a value of $1 per kilogram hydrogen. So clearly, innovations are needed both on the engineering side of things as well as the physical science side of things in order to make this process economical. So the main idea behind two-step stitch with redox-active metal oxides is that we take a metal oxide, we heat it to temperatures around 1350 C. Those are the conditions that we've used using concentrated solar heat. So in practice, this would mean putting it on sun somewhere like the National Solar Thermal Test Facility. So this leads to reduction of the metal oxide through the formation of oxygen vacancies and the production of oxygen gas. And then the material is cooled to about 850 C. And again, this is conditions that we've chosen. And then it's exposed to steam, and that leads to reoxidation of the metal oxide, not always to its original stoichiometric form. And this oxidation removes oxygen from water and produces hydrogen gas. So this process, as well as other details related to the design of materials for off-stoichiometric redox-active metal oxide-based stitch, is described in a recent book chapter we wrote, published in the book Solar Fuels. So please do check that out if you're interested. Sorry for the shameless plug. So one of the driving forces behind trying to replace CeO2 is that, number one, it doesn't seem like it's going to get to the hydrogen shot target, even through a series of different economic considerations, but also it's not a super flexible materials class. It has one structure and one cation site that could potentially be substituted. And while many different substituents and dopants have been considered, there doesn't seem to be one that outperforms just the binary compound itself. On the other hand, perovskites offer a lot of flexibility, as well as having quite a bit of popularity and recent knowledge about their various properties. So perovskites have the crystal structure shown right here. There is a simple cubic cell of A sites shown in blue, and then a B site at the center of that cube, or not necessarily a cube, as I'll say in a moment, which is that B site is surrounded by an octahedron of oxygen anions. So we can substitute on both the A and the B site, so it gives us double the flexibility of CeO2. And it also forms many crystal structures. I'm just showing 6 of the more common ones here, ranging from cubic and monoclinic to hexagonal and tetragonal. And these can also host things like octahedral tilting, which can reduce symmetry, and Jahn-Teller distortion, as well as different octahedral arrangements such as corner sharing, edge sharing, and face sharing. So there's really a lot of compositional, structural flexibility in perovskites, and this has been exploited to some extent in the development of materials like strontium, lanthanum, manganese, aluminum oxide, SLMA by McDaniel et al., as well as barium, cerium, manganese oxide, BCM by Barcelos et al. But despite this flexibility and the ability to tune and really try to hone in on the appropriate properties, there's really no perovskite that has supplanted CeO2. So here I'm showing on the right kind of the ascent towards that material that hopefully will supplant CeO2, starting with CeO2 in 2010, which offers 2.9 millimole hydrogen per mole atom ceria, which I'm just going to abbreviate from now on as MHMA. It's a mouthful, at what I'm calling perovskite conditions. So perovskite conditions are the conditions used to test BCM, SLMA, as well as calcium, cerium, titanium, manganese oxide, which is what we've discovered recently called CCTM. So at those conditions, it offers 2.9 MHMA. However, at its optimal conditions, at slightly higher reducing temperatures, for example, it offers somewhere around 10 MHMA. So SLMA was discovered in 2013. That offers 8.2 MHMA. BCM offers 7.3 MHMA. And more recently, our CCTM offers 10.4 MHMA, which, if you actually look, is better than cerium at its optimal conditions, or ceria at its optimal conditions. So we're excited, and we think that further testing hopefully will show that CCTM can perform in action in the real context as well as ceria. So how did we come to the composition CCTM? So here's our materials design blueprint. It really required some theoretical, it had a theoretical inception, and it had some experimental guidance along the way. Perhaps this is the ideal way to do materials design, but it was really an exciting process to be part of. So in 2020, my collaborators Sai Gautam, Gopalakrishnan, Ellen Stechel, and Emily Carter showed through computation that calcium, cerium, manganese oxide has an optimal 0K reduction enthalpy for two-step stitch. So that optimal reduction enthalpy, or the reduction enthalpy shown here on the y-axis, different cations that could dope at the metal site were focused on manganese, and these two red lines kind of highlight a region of optimal efficiency for stitch. So you can see that there are only a few that actually fall in this window, but the one we were most excited about was this calcium, cerium, manganese oxide, because it actually fell on the 0 Kelvin convex hull. So going with this, we collaborated with Bob Bell, Dave Ginley at NREL, and they tried to synthesize this material. But unfortunately, what they found was that upon synthesis, it wasn't single phase. It formed a ceria secondary phase, but also upon reduction oxidation cycling, that ceria phase actually grew in content. So unfortunately, the material couldn't withstand stitch conditions. However, it was some additional insight came from Ellen Stechel at ASU, who suggested that we potentially add titanium 4+ to stabilize manganese in the 3+ oxidation state, and also just generally the material overall, because calcium titanate shown here is a mineral. It is the mineral perovskite, and so after all, it's quite stable. So with that, initial theoretical input plus synthetic feedback and some additional just general materials intuition, we're able to arrive at a composition calcium, cerium, titanium, manganese oxide with 2/3 calcium, 1/3 cerium on the A site, 1/3 titanium, 2/3 manganese on the B site in a PNMA crystal structure, which is the crystal structure of calcium titanate. Here's a special quasi-random structure used to represent the solid solution. And that was simulated, but then it was made by Bell and Ginley at NREL, and powder XRD was done by Nick Strange at SLAC, and it was shown that the observed crystal structure of CCTM in a very similar composition almost nearly matched CCTM predicted by theory. Okay. So now, having shown that our prediction, manifested as a stable material that could be synthesized and, was characterized using XRD, we then went on to show theoretically that it could actually split water. And for us, that means calculating the neutral oxygen vacancy formation energy. But to do that, because we have a quasi-random structure, we had to consider a finite number of possible oxygen environments. So here I'm showing the crystal structure and focusing in on basically the frequency or percentage of different types of environments that could be present in the crystal. The x-axis shows the fraction of ceria, and the y-axis, the fraction of manganese surrounding the vacancy on the A and B sites respectively. So just to give you a better intuition for those, each vacancy shown here in black has 4 A site neighbors and 2 B site neighbors. The fraction of ceria on these A sites is X sub Ce, and the fraction of manganese on the B site is X sub Mn. So here are the reduction enthalpies for neutral oxygen vacancy formation energies at these different sites that we considered. And if we narrow in on the range that's optimal for Stitch, clearly we can see that the most frequently observed vacancies, with the exception of maybe these two right here at the top at, XMN equal 1, are all right in that window for Stitch, the optimal window for Stitch. So we have quite a large fraction of the vacancies that are present that could form in the crystal have the right reduction enthalpy. And this bears out in experiments. So laser heated stagnation flow reactor measurements done by Tony McDaniel Sandia show that when you reduce the material through, here you can see in black, it's heating the material from about 1123 Kelvin to 1623, which is 850 and 1350. That causes a loss of oxygen in the material, which upon introduction, cooling and introduction of steam, leads to the production of hydrogen in quantities of 10.4 and 10.7 mHma for the first 2 cycles. And this was all recently published. I couldn't list all the authors here because it wouldn't fit, but they're all listed on the first slide. And it was recently published in EES this year, so I highly recommend you take a look. There's a lot of other interesting insights in there, as well as some of the failed experiments that led to the arrival at this particular material. So please do check that out. Yeah, and so, yeah, so clearly we can see we have state-of-the-art water splitting at these conditions, which are lower than ceria. So that's really exciting. But as a physical chemist, there were some really unique redox characteristics of CCTM that I found truly fascinating. So not only did it seem practically interesting, but also physically and chemically interesting. So a real key feature of this material is that not only cerium 4+, not only is cerium in the 4+ oxidation state, which can occur in a perovskite, and for example, in BCM, and it's on the A site, which that is fairly rare. I actually don't know of another example of that. And it reduces not manganese 3+. If you actually look at the solid state binary reduction enthalpies for cerium 4 oxide and manganese 3 oxide, you'd actually expect that manganese 3 oxide would reduce more easily than cerium 4+. But it doesn't. But manganese 3 doesn't reduce, cerium does. And it does so actually even when it doesn't neighbor a vacancy. So we can do calculations that show even when we form a vacancy that doesn't have a cerium in its neighborhood, a ceria nearby actually reduces, and not the material, or not the cations that are closest. So here's showing that. So we do a calculation, we can produce a vacancy, and then we can actually calculate the charge density before and after forming the vacancy and take the difference. For the most part, we see polarization changes, which on average, at that site leads to no, change in the charge of the species. However, if we actually zoom in on a ceria that's fairly far away from the vacancy, you can see here there's a net gain of electrons, which if upon vacancy formation means that those electrons produced by the neutral vacancy are actually going to ceria. And so if we actually look here, that's about 8 angstroms. It's quite incredible that the charge redistributes itself in a way such that most of the additional charge localizes on a neighboring ceria. So you can see here that on average, manganese shown in purple as a function, they're basically the change in their absolute magnetic moments, which tells us about change in oxidation state as a function of distance from the vacancy. There's about a net 0 change in the overall manganese and B site sublattice redox. However, 2 ceria reduce far away from the vacancy. One that reduces the most is actually almost 8 angstroms away. And this idea that the manganese on the B site sublattice is doesn't really undergo redox on average. And the fact that cerium does on average reduce is shown in soft XAS spectra done by Sarah Schulde at NREL. So looking at the CE3DM edge, you can actually see a reduction in the binding energy of the electrons associated with the reduction of cerium. We don't see a similar feature in manganese, suggesting that it is only ceria that is really reducing, which is, again, really incredible. DFT with semi-local exchange correlation and Hubbard U corrections, which is just some fancy lingo for trying to make DFT better at doing redox. That tends to be qualitatively predictive for trends, but in this case, we were able to predict a structure, it was made. We were able to show that it could split water, and that bore out an experiment. And here, where really DFT could potentially break down in redox and electron redistribution, it suggested that cerium reduces, and that actually bore out in the experiment as well. So this constitutes a really, really exciting example of where theory was able to design a material with, of course, experimental input and guidance, but kind of a synergistic workflow to model ourselves on in the future. So to recap, we discovered CCTM with cerium on the A site, which was very interesting, and a stable crystal structure analyzed by X-ray crystallography that matched our predicted structure. Its reduction enthalpy is predicted from DFT to be ideal for stitch, and this was proven by stagnation flow reactor measurements, where CCTM actually surpasses SLMA and BCM under the same conditions, and just slightly surpasses ceria under lower temperature conditions compared to ceria's optimal conditions. DFT calculations also showed, as well as X-ray absorption spectra, that unlike other cerium-containing perovskites for stitch, like BCM, cerium is on the A site and in a high oxidation state, and despite that being in the A site, which tends to be a more chemically unreactive site, it accepts electrons even when it doesn't neighbor vacancies that form. This is really some interesting physics going on, and I think it warrants a lot more characterization in the future. But right now, our main goal is getting this material on Sun. With that, I just want to again thank all of my collaborators, and I will go through them by name. At Princeton, Gopalakrishnan Sai Gautam, who's now at IIT Bangalore, Emily Carter, Bob Bell, Sarah Schulde, Eli Nagrin, and Dave Ginley at NREL, Nick Strange and Sam Iacino at SLAC, Jamie Trindle, Josh Sugar, Anthony McDaniel at Sandia National Lab, and Ellen Stechel at ASU. This was a seedling funded by Hydrogen in the first round, funded by the DOE and ERE. The calculations were all done on the Eagle supercomputer, so really grateful for that. It was really a wonderful experience using that. And finally, I just want to mention that we were actually funded in the second round of the hydrogen seedlings to take CCTM from its original composition, the only one we really studied, and to study other compositions nearby and to try to optimize this material on both the atomistic, systems, and techno-economic levels. So if you're interested in joining potentially as a postdoc, please do reach out. We're trying to make CCTM a reality in a short time frame. So we're excited by anyone who might be interested. Anyways, with that, again, I'm so sorry I couldn't be there, but thank you for your flexibility in letting me provide this video. I hope you enjoyed the talk. And if you have any questions, you can bug my colleagues in the audience right now, or you can just send me an email later. I will be at the conference tomorrow, so we could also talk later. Thank you again, and enjoy the rest of the session.